Alright, well, I'm just going to go ahead and get started on this AP review problem. So just to read the problem for you, if you can see that, because this camera's terrible. In an electron microscope, a tungsten cathode with a work function of 4.5 eV is heated to release electrons that are then initially at rest just outside the cathode. The electrons are accelerated by a potential difference to create a beam of electrons with a de Broglie wavelength of 0.038 nanometers. Assume there's non-relativistic equations and they apply to the motion of the electrons. So to start off, it's asking us to calculate the momentum of the electron in the beam in kilograms meters per second. I'm going to start off here. I'm going to say that the wavelength is equal to h over p. So therefore, the momentum of the electron is equal to h over the given wavelength. So therefore, we can calculate the momentum as being h, which is a constant of 6.63 times 10 to the negative 34 joules times seconds. Sorry about that. Divided by our given wavelength, which is 0.038 times 10 to the negative 9th meters, which is nanometers. And that will give us the number of 1.74 times 10 to the negative 23 kilograms meters per second. That is our answer for part A. Alright, just to review, I'm just going to run through it one more time. There's the wavelength, which is h over the momentum. The momentum is h over wavelength. There's the numbers plugged in for h and wavelength, and there's your answer. Alright, to move on to B. It's asking us to calculate the kinetic energy of an electron in the beam in joules. So we're going to go with our basic kinetic energy equation, which is K equals 1/2 mv squared. And then again, to reiterate what the definition of momentum, it's P equals mv. So therefore V equals P over M. Let me move this over here real quick. There we go. So that gives us a velocity when we plug in for P and M. So P is equal to our given from A, which is 1.74 times 10 to the negative 23rd kilograms meters per second, divided by M, which is a given mass of an electron, which is 9.11 times 10 to the negative 31 kilograms, which gives us a value. You can see the equation, it's right there. Which gives us a value of 1.91 times 10 to the 7th meters per second. Okay, now we're going to plug this back into this K equals mv squared equation to find our kinetic energy. So K equals 1/2. So our given mass of an electron, which we already plugged in here, is 9.11 times 10 to the negative 31. So I'll just write that again. We're going to multiply that by the velocity that we just calculated, which is that. So 1.91 times 10 to the 7th, then we're going to square that value, which is going to give us 1.66 times 10 to the negative 16th joules. And that is our answer, boys and girls. Okay, so just to run over it, k equals 1/2 mv squared. Momentum is mass times velocity. Velocity is momentum over mass. Plug in for momentum and mass to get our velocity, which we plug into our kinematics equation, which gives us that. Alright, so for part C, part C is asking us to calculate the accelerating voltage of the given thing. So we know that K equals QV, therefore V equals K over Q. So K, which is what we calculated in the previous portion of the problem, is 1.66 times 10 to the negative 16th joules divided by Q, which is the given charge of the electron, which is 1.60 times 10 to the negative 19th coulombs, which is equal to 1.04 times 10 to the third volts, and that is our answer. Pretty simple. So K equals QV, therefore V equals K over Q. Plug in for the solved value of K and our given value of Q from our green sheet, which gives us that. Alright, part D. So part D is saying that suppose the light instead of heat is used to relate the electron or release the electrons from the cathode. What minimum frequency of the light is needed to accomplish this? Okay, so we're kind of going to use some reverse psychology here. So K max equals HF minus the work function. Okay. Now we know that at a minimum, K max is going to be equal to 0. So therefore, the work function is equal to HF. So in order to solve for our given frequency, F is going to be, work function over H. Okay, and then when we plug in for that, the given work function from the problem, which is 4.5, so 4.5 eV over H, which is a given value, which is 4.14 times 10 to the negative 15th eV times seconds. Right there. And that's going to give us F, which is 1.09 times 10 to the 15th hertz. And that is all. So just to review, Kmax is HF minus the work function. So at a minimum, Kmax is going to be 0. So our work function is equal to HF, which through simple algebra, F is the work function over H. Plug in for the work function in H, which gives us the frequency of 1.09 times 10 to the 15th hertz. And that wraps us up for this problem. Thank you.